This is a video about sumatriptan, a drug used for the clinical treatment of acute migraine. There are two main classifications of migraine: migraines with aura or migraines without aura. Both migraines often cause nausea and vomiting, but the most common symptoms are severe headache starting on one side of the head, which may move and surround the head as symptoms worsen. Some patients may lose tolerance to noises and smells. Migraines with aura occur in 30% of patients and have added visual symptoms. These migraines occur less regularly, but have more severe symptoms such as temporary blindness and tingling across the whole body. Though the exact cause is unknown, migraines have been linked with temporary changes in blood vessels and nerves in the brain, including serotonin receptors. Other risk factors include genetics, stress, and many more have been linked to the condition. For many years, it was thought that vasodilator drugs cause migraine, whereas vasoconstrictor drugs can reduce pain. The ideas that serotonin was related to the cause of migraine went back to the 1960s. Two independent studies conducted showed that intravenous 5-HT, or serotonin, could stop migraine attacks, leading Glaxo scientists Patrick Humphrey and co. to investigate serotonin receptors in 1972. As serotonin is a basic and non-lipophilic substance, it has poor movement across the blood-brain barrier, leading Humphrey and his team to believe that serotonin causes vasoconstriction within the cranial vessels, which become distended and inflamed during migraines. The team started looking for a selective agonist that would copy the beneficial effects of serotonin whilst avoiding its non-beneficial effects, such as platelet aggregation. With serotonin as a lead compound, a long path of drug development began. It was found that some serotonin, or 5-HT receptors, cause vasoconstriction, whilst some cause vasodilation. 5-HT1B receptor, a vasoconstrictor, was used to screen the activity of many analogues of serotonin. Firstly, to establish the structural features needed for potency and selectivity, the research team carried out systematic changes to serotonin. The hydroxyl group of serotonins was replaced with a hydrogen, or other substituents. This caused reduced activity at DSV receptor, 5-HT1-like receptor, compared to serotonin. 5-carboxamidotryptamine, 5-CT, was discovered to be as potent a DSV receptor agonist, but was 25 times less potent than serotonin as a 5-HT2 agonist. Unfortunately, 5-CT was found to be an agonist of receptor 5-HT7, causing unwanted vasodilation effects. Replacing the carboxamide group of 5-CT with other electron-withdrawing substituents resulted in some selectivity. A 5-CT homologue, eloquently named 5-carboxamidomethyltryptamine, gave the research group a new lead compound, which had 20 times more selectivity at 5-HT7 relaxant receptors and no activity shown at 5-HT2 receptors. Further modification led to the discovery of AH25086, which was 4 times less potent at DSV receptors and inactive at many other 5-HT receptors, such as 5-HT7. AH25086 was found to resolve headaches and reduce migraine symptoms when given intravenously, but was not orally available. Replacing the carboxamide group with a sulfonamide group resulted in similar binding interactions, but the primary amine group was still too susceptible to metabolism. Replacing this with a tertiary amine led to the discovery of sumatriptan, which was found to be potent, effective, orally bioavailable, and had far fewer side effects than previous analogues. Following human toxicological evaluation testing, the drug was evaluated for therapeutic effect. In Germany, a non-placebo-controlled study was conducted during 24 migraine attacks by administering 2 mg of IV sumatriptan. 71% of patients experienced rapidly relieved symptoms, and the other patients experienced partial relief. Eventually, the drug was formally launched in 1991. To model the binding of sumatriptan with 5-HT receptors, many dynamic simulations with 3D models have been conducted. Researchers Smolyar and Osman found that the cationic side chain of protonated sumatriptan forms ionic interactions with aspartic acid 111 in the transmembrane helix of the 5-HT1D receptor. They also hypothesized hydrogen bonds between the indole NH of the ligand and the carbonyl backbone of leucine 115, the sulfonamide NH and the carboxylate of aspartic acid 339, and the sulfonamide SO and the hydroxyl group of tyrosine 346, as well as hydrophobic interactions between the sumatriptan indole ring and aromatic rings in phenylalanine 317 and tryptophan 343. Another model, by Bremner et al., agreed with the ionic interaction at aspartic acid 111, but suggested that hydrogen bonds form between the indole nitrogen and serine 12. They also believed that the indole group was hydrophobically anchored by tryptophan residues in helices 4 and 6, as well as by phenylalanine 18. They also hypothesized that the sulfonamide side chain folds across the indole ring to allow optimum accommodation in the receptor binding site. Further hydrogen bonds between the sulfonamide nitrogen and serine 21, plus the sulfone oxygen and threonine 6, were thought to stabilize this conformation. 5-HT1B and 1D are almost pharmacologically indistinguishable due to 68% amino acid sequence homology. Hence, sumatriptan will bind similarly to the 5-HT1B receptor. Sumatriptan is synthesized from the commercially available N-methyl-1 4-nitrophenyl methane sulfonamide starting material. Using nitrous oxide, made in concentrated hydrochloric acid at -5 degrees Celsius, diazotization occurs. The diazonium group is then reduced to the aryl hydrazine product. The aryl hydrazine is converted to an aryl hydrazone in a condensation reaction with another commercially available reagent, 4-chloro-1,1-dimethoxybutane. An acid catalyst is next used to encourage an internal ring-forming reaction known as a Fischer-indole synthesis. This requires no other reagents, making this step relatively cheap in terms of drug synthesis. Converting the chloro group to a primary amine is a simple substitution reaction, but the final conversion of the primary amine to a tertiary amine involves an Eschweiler-Clark methylation. Using formaldehyde to introduce a carbon and sodium borohydride to reduce the intermediate. This reaction stops at the tertiary amine, at which point the formaldehyde can no longer introduce a carbon, as the nitrogen cannot stain the 5 bonds necessary for the intermediate. This selectivity means the reaction stops at sumatriptan. Unfortunately, this original synthesis had a low yield and several impurities. The main impurity was prevented by adding an ethyl ester protecting group to the nitrogen of the sulfonamide group. This gave rise to a one-pot process from hydrazone formation to indole synthesis, with a yield of 50%, followed by the removal of the protecting group by potassium hydroxide. However, a new impurity became prevalent. The solution was adding another ethyl ester protecting group to the aryl hydrazone product. This protecting group ends up at the C2 position of the indole, resulting from a selective 80% yield in the Fischer-indole synthesis. The first protecting group is still removed by the basic potassium hydroxide, whereas quinolone and copper powder are used in reflux to remove the second. The result is the target sumatriptan molecule.
Sumatriptan is a highly selective agonist of 5-HT1B and 5-HT1D receptors, with very little activity at other 5-HT receptors. 5-HT1B and 1D are negatively coupled at adenate cyclase, which when then stimulated decreases levels of cyclic AMP. Normally, tryptophan is converted to 5-hydroxytryptophan by tryptophan hydroxylase. Aromatic amino acid carboxylase then converts 5-hydroxytryptophan to 5-hydroxytryptophamine, serotonin. This is then released across the synaptic cleft where it stimulates the presynaptic 5-HT receptors. This stimulation is then terminated by reabsorption via the reuptake transporters, or diffusion away from the synapse. Sumatriptan's binding to 5-HT1B and 1D receptors increases stimulation and causes vasoconstriction. Commonly reported central nervous side effects of sumatriptan include disturbances and headaches. And much like the mechanism of action, there is no definite mechanism of central nervous system side effects, as it's still unclear. One of the considered possibilities for these side effects was thought to be due to binding of non-5-HT receptors. However, studies have shown that at low nanomolar range, sumatriptan showed a lack of affinity to other serotonin receptors. Another popular suggested theory was that by crossing the open blood-brain barrier during a migraine attack, sumatriptan could then enter the central nervous system, therefore causing its side effects. Although nowhere as frequent as central nervous system side effects, coronary side effects have also been reported after the administration of sumatriptan. As well as these side effects, sensations of tingling, heat, heaviness, pressure, and tightness of any part of the body have also been reported and are said to be caused by coronary vasoconstriction. The original concept of sumatriptan was to design a selective 5-HT1D receptor agonist, but in humans, 5-HT1D and 5-HT1B receptors are closely related, and therefore sumatriptan has similar activity in both these receptor subtypes. Triptans can bind to 5-HT1B receptors, causing not only vasoconstriction of cranial arteries, but those of the coronary arteries, which causes reduction of blood flow and therefore leads to coronary adverse effects. Triptans can bind to 5-HT1B receptors, causing not only vasoconstriction of cranial arteries, but also those of coronary arteries, which can cause reduction of blood flow and therefore lead to cardiovascular adverse effects. Due to sumatriptan binding to 5-HT1B receptors, coronary side effects can be described as off-target. However, it's been said that sumatriptan is safe and concluded that among patients with known or suspected coronary artery disease, triptan use doesn't appear to correlate with an increase in frequency of serious cardiovascular events. Triptans are selective vasoconstrictors of cerebral arteries over coronary arteries, but caution should still be exercised with patients defined at low risk of coronary artery disease, or at best even avoided, as there is evidence supporting contraindications in these risk patients.